We're going to take a look at graded muscle contractions and how the number of muscle fibers contracting affects the force of contraction produced. Graded muscle contractions allow you to produce different amounts of force with muscle contractions, allowing you to, for example, pick up a pen versus picking up a child. And there's two things that allow you to produce different amounts of force. So one would be the amount of force produced by the individual muscle cell itself. And then the second one would be the number of muscle fibers that are contracting. So that's what we're going to be focusing on in this video. So the number of muscle fibers that are contracting, that's affected by recruitment. In recruitment, we're going to increase the number of motor units, and that involves the number of muscle fibers that are going to be stimulated. So the more muscle fibers that are contracting, the greater amount of force that you're able to produce. So remember that our motor unit is just the somatic motor neuron with all of the muscle fibers that it innervates. So we've got motor unit X up here, and then we've got motor unit Y down here with the lighter tan color. And if we stimulate motor unit X to contract, it's innervating 5 muscle fibers. So we've got these darker red fibers, and it would generate this amount of tension or force. And then motor unit Y is going to innervate 7 muscle fibers. And because you're having 7 fibers contracting instead of 5, motor unit Y would generate more force than motor unit X. And if you stimulated both motor unit X and Y to contract at the same time, so all 12 fibers would be contracting at once, that would generate the most force. So we actually have different sizes of motor units. We have small and large motor units. So let's take a look at these small motor units first. So they're going to be innervating a smaller number of muscle cells, and the muscle cells that they do innervate have a smaller diameter. So they're going to be generating less force. So they're going to be used for less forceful contractions and more delicate movements. And the neuron that innervates them is going to be easier to stimulate, so they're going to be recruited to contract first. And then the large motor units, they have a larger number of muscle fibers that they innervate, and then also the muscle fibers have a larger diameter. So both of those things will allow these larger motor units to generate more force. And so they're going to be used to generate more force with forceful contractions, and will be used for movements that require a lot of strength, so maybe like lifting weights. And they're going to be innervated by a motor neuron that is harder to stimulate, and so they're going to be recruited last to contract. So having these different size motor units leads us to this size principle. The size principle is really important to know. So I would definitely know this for the exam. And if you look at the name, it tells you what is going on. So the size principle just says that when you go to use your muscles, you're going to recruit the smaller motor units to contract first. And if that's not enough power and you need more force, then you're going to recruit the larger motor units to contract next and generate more force to help you out. Okay? And so this is going to allow you to produce these graded muscle contractions. So this is one way you can do this with this size principle. So let's take a look at these motor units here. We've got 3 different sizes. We have motor unit X, and this is a small motor unit. We're only innervating 3 muscle fibers, and they're all small diameter. So this motor unit X is not going to generate much force. And then motor unit Y, we're innervating 5 muscle fibers, and they're larger diameter than we see in motor unit X. So motor unit Y is going to generate more force than motor unit X, so it's kind of an intermediate size motor unit. And then motor unit Z is the largest of these 3 motor units. So we're innervating 7 muscle fibers, and they're the largest diameter out of all 3 of these motor units as far as the muscle fibers. So motor unit Z would generate the most force out of all of these. So let's say that you need to, pick up a pen, for example. So you would recruit motor unit X first, and that probably would be enough force to pick up a pen. And that would be all you would need. Okay, so you can see down here on our graph, here's motor unit X contracting, and that's how much force you would produce, which would be fine to pick up a pen. All right, but let's say that now you're going to pick up, a couple textbooks. Okay, that's a bit heavier. So we're going to recruit motor unit X to contract first, and we realize that, oops, that's not enough force to pick up these textbooks. So now we're going to recruit motor unit Y to also contract at the same time. So we're going to have motor units X and Y contracting at the same time, and that's going to generate enough force to pick up these textbooks. All right. And now let's say that we're going to go lift up a 5-year-old child. Okay. And so when we go to pick up the child, we're going to start with motor unit X, not enough force. So now we're going to recruit motor unit Y to help us out. But again, not enough force with X and Y contracting. And now we're like, okay, we need to recruit motor unit Z to help us out. So now we have motor units X, Y, and Z all contracting at the same time. And now we're able to generate enough force to pick up the child. Okay, so that's the size principle. It's just saying that when you start a muscle contraction, you're going to recruit the smallest motor units to contract first. And if that's not enough power, then you'll recruit the next largest motor unit to contract. And if that's not enough power, then you tell the large motor units to help you out and contract. Okay, so that's the size principle. All right, the other thing that we see with our motor units, if you have sustained contractions, so maybe you're carrying some groceries in to your house, you're going to rotate which motor units are contracting and which ones are relaxing, because you don't want them to all contract at once, because then they're all going to relax at the same time, and then you would drop your groceries. Okay, so what we're going to do is we're just going to activate our motor units on a rotating basis. So maybe we're going to activate motor unit 1 and have those muscle fibers contract, carry the groceries, and then we'll activate motor unit 2 to contract while motor unit 1 then relaxes, and then motor unit 3 will then contract and take over while motor unit 2 relaxes, and then we'll be back to motor unit 1 again. It'll contract, take over, carry the groceries. And so this will help prolong the muscle contraction and allow you to get your groceries in the house without dropping them. And it also keeps the contraction smooth, because it just looks like your muscle is like one long continuous contraction the whole time, but actually some of the motor units are contracting, some are relaxing, and then they switch off. And it's not like they're all contracting and all relaxing at the same time, which would cause you to drop things and would cause jerkiness in your movements as well. Okay, let's just take a look at a couple of graphs here. These are looking at some isotonic contractions. So remember, in isotonic contraction, you're able to overcome the load and lift it, and the muscle will shorten while the tension, the amount of force that you produce, will stay the same. Okay, so what we're looking at in this graph is we've got the time on the bottom, and then the y-axis we've got the distance shortened, so how much the muscle is going to shorten. And then the slope is the velocity or the speed of shortening. Okay, so how fast the muscle will shorten. So the green graph is just showing that if your muscle is shortening and you have zero load. So maybe you're just raising your arm above your head, okay, and you have nothing in your hand. So that would be really easy to do, right? So you can do that really fast, and you can get your arm all the way up above your head. Okay, so you could go all the way up and do that really fast, and you could do that, for a long period of time. That's shortening. Okay. All right, now let's say that in your hand, let's put a textbook. It's a little bit heavy, and so it's going to take a little bit to start, overcoming that load. So you get a little bit of an isometric contraction first, and now you start to shorten, and now you start lifting it above your head, but you're not going to be lifting it as fast as you did when your hand was empty. And then, maybe it's a big textbook, and maybe you can't get it quite all the way above your head. Okay, so you don't shorten your muscle as much as you did when you had nothing in your hand. Okay, and then this red one would be like a heavy load. So I don't know, maybe we put, a weight in your hand. Maybe, there's a 20-pound weight or something, in your hand. And so now you're going to lift that above your head. And so now it's going to take more time to start overcoming that weight before you start shortening your muscle. And because it's heavy, it's going to take longer to shorten your muscle and raise that weight above your head. And then plus you're not going to be able to raise it very far above your head. Well, at least I couldn't, because my muscles are pretty wimpy. And then also, I'm not going to be able to lift that weight for very long either. So it'll be much shorter time that weight's going to be above my head if I have this heavy load. So this is just, kind of common sense. We've all experienced this. Heavier things, you're going to lift slower. You're not going to be able to lift it as high. And not for as long. So that's all this graph is telling us. All right, and then this last graph is just, they call it a load velocity curve. So we've got on the bottom increasing weight of load. So our load is getting heavier and heavier. And then on the y-axis, we've just got the shortening speed of the muscle. Okay, so over here on the left, we start with a zero load, so like nothing in your hand. Okay, so you can shorten your muscle really fast and, lift your hand really fast above your head. So maximum speed, you could shorten. But as the load gets heavier and heavier, your muscle is going to shorten and lift that load a lot slower, isn't it? Okay, if you put heavier and heavier weight in your hand and you had to lift that above your head, you're going to get slower and slower at lifting that above your head until you reach a point here where you're not able to lift that load, right? It's too heavy. Okay, you can't overcome the weight, and what's happened is that load is so heavy that you've now turned that isotonic contraction into an isometric contraction, right? Because you're no longer able to shorten your muscle and it stays the same length. And so now it's an isometric contraction. So before you were able to shorten it, okay, so you were shortening here And it was isotonic, but then when you're not able to shorten, now it turns into isometric.